Hello, let us go with next topics, and as I anticipated, it is an interesting and exciting topic this time. And the title of this chapter is Continuous Functions on an Interval. So you know what is a continuous function, you know what is an interval, and what I want to tell you now is that for continuous function on an interval, it holds what you probably heard in high school as a characterization of continuous functions. And the characterization is this. There is a function, a continuous function, whose graph can be drawn keeping the pencil on the sheet. Okay? If the domain is not an interval, but for instance the union of two disjoint intervals, of course this is not possible. If it is a set of isolated points, like for sequences that are continuous functions, I recall it, this is not possible. But for continuous function on an interval, this is possible. And for these functions, there are three theorems that are very important, and I will introduce you these theorems before stating them and proving them. The first one is the so-called theorem of existence of zeros. This theorem, which as far as I know is due to Viastras, he was the pioneer of the continuous function, says the following things. If you have a function defined on a closed and finite interval, a, and b are real, and you know that f of a is negative and f of b is positive, then there must be a point where f is equal to 0, an internal point of the interval, of course, and this is really apparent if you try to draw a graph of the function, keeping in mind that you can do it by keeping the pencil on the sheet. And so there is at least one point where you have f equal to 0. In this picture, I drew 3 points in which this happens, but at least one must be there, because when you keep the pencil on the sheet, you have to cross the interval. Okay, this is simple to understand, and not so simple, but extremely beautiful to prove. Okay, so I will prove it. Second, this is the theorem of Viastras. Again, this is officially by Viastras. When you say Viastras theorem, you mean this. That says that there is a maximum. Again, the interval must be closed and finite. So a and b are real numbers. Here you have the interval. And again, when you try to draw the graph of a continuous function, again, you are forced to foresee a maximum. Here is the maximum of the function, and of course, symmetrically, you will be obliged to find also a minimum that is here. Maximum and minimum. Third theorem is due to Heine and Cantor, again Cantor. and it is on uniform continuity. So when you have a function that is continuous again on a finite and closed interval, so you go from continuity to uniform continuity. What is uniform continuity? Of course, you don't know it. It is a stronger version of continuity, and this is useful from a theoretical point of view. So in all this theorem, I underline this. The theorems, the three theorems, require the domain, the interval, to be closed and bounded. Namely, the domain E is equal to the interval AB with both A and B real numbers. Okay, and so the first existence of zeros will be an important theorem. We will prove it. And I will ask you to know the proof. Viastras theorem again, prove today. Heine-Cantor, it is useful only in one specific occasion in this course, which is the proof of the fact that continuous functions on a closed interval, closed and finite interval, are integrable. Okay? This is the only necessity that we have to introduce this theorem and to introduce the idea of uniform continuity. Okay, uniform continuity is very important from a theoretical point of view, but for our course, its relevance is not so widespread. So what I will do is to introduce this theorem. We will see whether with proof or without proof. The proof is very nice, but not so easy. We will see it when doing the integrals, which means next week. Okay, in the lectures of December 23rd. So we will see it. For today, we will focus on the first two theorems. Okay, so we start with the first one. I already gave you a picture, and the first theorem of this chapter is on existence of zeros. The statement of the theorem is: let A and B be two real numbers with A less than B, and the function f from the closed and bounded interval AB to R. This has to be continuous on the whole interval AB. Oh, sorry. Moreover, f in A is less than 0, and f of B is larger than 0. Okay, so this is the idea you should keep in mind. So f of A less than 0, f of B larger than 0. Then there exists point C in AB such that f of C is equal to 0. So the first, before giving you the proof, I will start by giving you the idea of the proof that probably will make it easier for you to follow the proof. So I find this proof, I already told you, very beautiful and very instructive too. We will use some tools from sequences and so on. So you here have your interval AB, and you have a function here. Oh, let me suppose you don't know the function, but in order to reason a bit clearly, let me draw this function, and you just know at the beginning that f of a is less than 0, f of b is larger than 0. So what you do, you go to the middle point, and you call it, and the middle point a plus b divided by 2, and then you check whether in this middle point the function is larger or smaller than 0. Then you find that this is larger, and now you change some names. You say that a is equal to a1, and this point here is called b1, and then you focus on the interval a1, b1. Okay, this is the key passage. Okay, you start from the interval ab, and just considering whether the function is positive or negative in b1, you are able to reproduce the starting situation on a smaller interval, an interval which is the original one divided by 2. Okay? This is a gain. We will say that this is a gain. Of course, it may be that f of b1 is equal to 0. In this case, it is finished. Okay? So now, again, you are in this situation with a function, so focus on this interval, a1, b1, and you have a function which is negative on the first extreme of the interval and positive in the second one. So it is exactly the same situation as before. So what can you do? You go to the middle point of this new interval, middle point that is here, and then you check whether the function here is positive, 0 or negative, and what you find is that it is negative. Okay, so you change again the name, and this point you call it A2, B1 now is called B2. This is just a matter of names. And now at this step you focus on what happens in the interval A2, B2. Okay? So now you're studying a situation which is analogous to the starting situation, but in a smaller interval, which is 1/4 as a size of the original one. And again, you repeat the algorithm. So you look at the middle point here. The middle point function is negative again. So you call this middle point A3, and this is again B3. And now you focus on the interval A3, B3. So I stop here. You repeat this construction at every step, and what you find is that you end up with two sequences. AN, which is the sequence of the left extremes of the interval that you are considering, so you have A1, A2, A3, and so on, which is monotonically increasing. And Bn, which is the sequence of the right extremes of the interval, and here is the sequence B, B1, B2, B3, which is monotonically decreasing. Okay? So, of course, they are also bounded, so they converge. And what you have to prove is that the monotonically increasing sequence AN and the monotonically decreasing sequence BN converge to the same limit. So you have AN tend to some L, BN tend to some L, which is inside the interval, and one finds that f of L is equal to 0. This is the scheme. This is the scheme. And of course, if you understood this scheme, then you are already able to write down the proof. But the proof is complicated, it has many passages, so I will write it extensively for you. It will be a bit long, but in my opinion, it is a task that has to be accomplished. If you did not understand the schema, keep it in mind and probably it will clarify a bit of the passages I will do now, okay? But if you did not understand now the scheme of the proof, my suggestion is to listen to this part of the video again and again, because it is really useful to understand what follows. And if at an oral exam I will ask you to give me the proof of this theorem, you can skip this part and go directly with the proof, which I will give you now. So the proof is the following. Let us consider the point C. It is the middle point of the original interval, so it is A plus B divided by 2. We distinguish between 3 cases. The first case is f of c is equal to 0. Then the proof is complete. We found by luck. We found by luck a point where the function vanishes. Second is f of c is less than 0. And this is the situation, f of c is less than 0. This is the situation, here you have c. And so now we change names, we give new names, and we say that a1 is equal to c, b1 is equal to b, so c is now a1, b is b1, so we focus on the interval a1, b1, and we have so that f of a1 is less than 0, f of b1 is larger than 0. So the new interval on which we focus is a1, b1, and of course the size of I1 is b1 minus a1 divided by 2, and a is less than e1 and b1 is equal to b. Third case, which is still symmetrical with respect to the second, f of c larger than 0, and the picture here says the following. Here is C, and this time we baptize, A1 to be equal to A and B1 to be equal to C. So now the interval on which we will focus is again A1, B1, and we have that f of A1 is less than 0, f of B1 is larger than 0, and A1 is equal to A, B1 is less than B, And again, the size of the new interval is half of the size of the previous interval. Sorry, it is not b1 minus a1 divided by 2, is b minus a divided by 2, because it is b1 minus a1, which is b minus a divided by 2. And so the first step is finished. Now we are reduced to a half of the original interval, and so we go further with our algorithm. Algorithm goes further in cases 2 and 3. In these cases, we define or denote C1 to be equal to A1 plus B1 divided by 2. So the half of the new interval. So let us go to previous pictures. This will be C1 in this case and C1. So we focus on the interval A1, B1, and we repeat what we did before. And then there are three cases. The first case has f of C1 is equal to 0, and then we say that the proof is complete. Second, f of C1 less than 0, and we define again A2 equal to C1, B2 equal to B1, and f of A2 less than 0, f of B2 larger than 0, and the new interval we will focus on is I2 is equal to A2 B2, and the size of I2 is B2 minus A2, which is B1 minus A1 divided by 2, so B minus A divided by 4. Okay? In the third case is when f of C1 is larger than 0, and this time A2 will be the same left extreme of the interval as before. A2 is equal to A1, and B2 is equal to C1, and here we have f of A2 less than 0, f of B2 larger than 0, and as before, I2, the new interval, is the interval closed and bounded A2, B2, and again the size is B minus A divided by 4. After the two-step, the size of the interval we are considering is 1/4 of the original interval. So now what you understand is that we iterate the procedure If at the nth step we found that f of Cn, the middle point, equal to 0, then the algorithm stops. And the theorem is proven. On the other hand, so if on the contrary, for every n, f of Cn is not 0, we construct two sequences. The procedure give us automatically two sequences. Sorry, we construct. The first sequence is AN, which is the sequence of the left extremes of the considered intervals. And the second sequence is Bn, which are the right extremes. So by construction, the sequence AN is monotonically increasing. And bounded since for every n, of course, AN is in the interval AB. Then AN must converge to some L in AB. So in a completely analogous way, Bn is monotonically decreasing. And bounded too. So Bn converges to, and we have that Bn tends to some k in AB. Finally, AN is always less than Bn, which implies, by permanence of sign, if you want, that the limit of AN cannot exceed the limit of Bn. Okay? So there are these two limits. So the situation is this. There are these two limits. This is the AN, and these are the Bn. Sorry, Bn monotonically decreasing. So AN tends to some k, goes to some L, Bn tends to some k, and now we want to compute the distance between k and L. Of course, L cannot exceed k, so k minus L is non-negative. And let me write k minus L like k minus Bn plus Bn. And here there is minus L, and let me add plus An, and here minus An. Okay? Then we use 2 times the triangular inequality, the first triangular inequality. and this is less than k minus bn plus bn minus an plus an minus L. So this is true for every n. And now notice that k minus bn, this distance, goes to 0 as n goes to plus infinity. Because bn tends to k, also an tends to L. And here, bn minus an, this is equal to b minus a divided by 2 to the nth power, which is the width of the, this is the width of the interval an equal to an bn, and this goes to 0 too. So notice that here we have a quantity which is non-negative, and it is smaller than any element of a sequence that goes to 0. Okay, you can see it as an application of a two Carabinieri theorem when two sequences are constant. Okay, this is, you can interpret 0 as a constant sequence, and also k minus L. So what you have that by double comparison, the sequence k minus L, which is a constant function, so it tends, a constant sequence, so it tends to k minus L, is between 0 and 0, and so k minus L is equal to 0. So k is equal to L, so the limits of the two sequences an and bn are the same. Now you have to compute what is f of L. And here you have that f of L can be seen as f of the limit of an. And now you use the fact that f is continuous. We never used that. If f is continuous, the limit can be pushed here, outside. Okay? This is equal to the limit of f of an. And since f of an is always negative, this is less or equal 0 by permanence of sign. So this is permanence of sign. And this is continuity of f. Oh, sorry, this equality here. But f of L is equal to f of k, because L is equal to k. K is the limit of bn, and this is the limit of f of bn. Again, by permanence of sign, this is larger or equal to 0. So you have then f of L is between 0 and 0, and the only possibility is that f of L is equal to 0. And this is the end. To be coherent with the proof, I will change the notation in the statement. So let me say there exists L. Sorry. Okay? The message is the same. There is a point where the function vanishes, but let me call it like in the proof of the theorem. Okay, I stop here this recording and I will come immediately to the next one.